He had already passed the point where most comets begin to die. The most hostile region of the orbit, where the sun usually tears icy surfaces apart, triggers fractures, and turns entire nuclei into clouds of debris. After this critical point, the expectation was simple. 3I Atlas should enter a predictable phase of gradual weakening. Less activity, less brightness, fewer surprises. But what emerged in the following observations moved in the opposite direction, and that's what truly caught scientists' attention. On November 30th, 2025, the Hubble Space Telescope observed it again and found something hard to ignore. A gigantic luminous structure surrounding the nucleus, continuous, clean, and with an unusual level of organization. The shape was striking, a kind of glowing teardrop suspended in space, with a rounded region near the center, and a long, narrow extension tapering to a point. And that point was facing directly toward the sun, forming a rare antitail. This detail breaks intuition because the basic rule is straightforward. Comet tails point away from the sun, pushed by radiation and the solar wind. Antitails do exist, but they are usually faint, temporary, and highly dependent on the viewing angle. In the case of 3I Atlas, it was not a subtle effect. The antitail dominated the image and appeared integrated into the structure itself, as if the entire glowing teardrop were organized around that direction. Even before these images, one conclusion was already practically consolidated by the end of 2025. 3I Atlas does not belong to our solar system. Its hyperbolic trajectory reveals an interstellar visitor. That places it in an extremely rare category, alongside Oumuamua and 2I Borisov, and interestingly, each visitor on that list arrived by breaking expectations in a different way. Oumuamua, with no visible tail, Borisov, with unusual chemical composition, and now 3I Atlas, displaying an appearance that didn't seem to obey the most extreme moment of its solar passage. Post-perihelion, in theory, should be the calmest phase of the journey. The worst would already be behind it. Solar influence would decrease, and activity would tend to drop. But this is precisely when the story became more unsettling, because Hubble's observation was exceptionally clean. No atmospheric distortion, no typical ground-based telescope noise. What appears in the images is direct and valuable information, and intact post-perihelion records of interstellar objects are extremely rare. The observed scale was colossal. The rounded luminous region was about 25,000 miles wide, while the narrow feature stretched for nearly 37,000 miles. And it was not a diffuse cloud. The brightness was concentrated, with relatively well-defined edges. In typical comets, dust and gas form thin, hazy, irregular tails that fan out and disperse over time. 3I Atlas, however, seemed to maintain cohesion beyond the norm. This contrast matters because it changes the type of question you can ask. A loose tail is usually interpreted as lightweight debris reacting to the sun. A compact, directional, and persistent structure demands more caution. It suggests there may be a mechanism sustaining that pattern even after the object passed peak heating. There is also a subtle detail reinforcing why this discussion gained momentum: the very cleanliness of the structure. When a comet releases fine dust, the distribution typically creates more irregular gradients, with regions fading unevenly. In 3I Atlas, the brightness appeared smoothly continuous, as if there were a more consistent emission pattern than usual. That alone proves nothing, but it is the kind of difference that makes researchers return to basics and ask, are we interpreting correctly what we are seeing and what is actually producing this light? Another reason this case is so valuable is historical. Interstellar visitors pass quickly and are difficult to observe for long. When the object survives perihelion and remains observable, scientists can finally see the result of solar stress instead of merely assuming it. That allows models to be tested more seriously, comparing before and after, rather than relying on a single snapshot at one moment in time. It is also worth remembering that even when the explanation is entirely natural does not mean simple. An object formed in another stellar system may have different porosity, different ice composition, and surface layers processed by cosmic radiation for millions of years. That can change how it releases gases, how dust detaches, and even how jets organize. Sometimes what looks like a puzzle may simply be nature showing that our examples are still limited. That is when direction became the center of the debate. Antitails, when they appear, are often explained as geometric effects. Dust distributed along the orbit seen under a specific alignment, creating the appearance of a beam pointing inward. In those cases, the effect tends to change as the geometry changes. But in 3I Atlas, the antitail did not look like a temporary visual trick. It was bright, long, and integrated into the teardrop shape. Concern grew when scientists compared observations from July 2025 with the post-perihelion image from November. Change was expected. Perihelion is not a gentle milestone. It is the most punishing phase with intense radiation, soaring temperatures, and rapidly increasing internal stresses. Even when a comet survives, its appearance usually evolves. Tails change thickness, bright regions shift, jets vary, asymmetries appear. In 3I Atlas, the overall shape seemed surprisingly stable. For many, that stability was the truly uncomfortable point. If extreme heating had created the structure, it would be reasonable to expect it to lose organization once the sun stopped forcing the system. If it were fragile, it should blur and spread over time. But the object appeared to maintain the same logic of shape and direction over months, crossing both sides of perihelion. At that moment, the question changes in nature. It stops being, how did it survive, and becomes, why didn't it change? And when the question changes, the hypotheses change as well. An alternative interpretation that gained attention came from Avi Loeb. Instead of assuming the glowing teardrop is mainly fine dust, he suggested the structure could be shaped by larger, more solid fragments separating from the main body. Such fragments would behave differently. They would be more cohesive, would not spread quickly, and could sustain a more compact distribution. If those fragments released gases unevenly, that could generate a small non-gravitational acceleration, a subtle push capable of altering the trajectory without requiring anything mysterious. It is important to say, non-gravitational acceleration is documented in comets, linked to sublimation and gas release. What Loeb highlighted as out of the ordinary was the organization and persistence of the system, as well as a specific geometric point. Before the post-perihelion image was released, he had published models predicting where an antitail should appear under his interpretation, and the observed position was close to that prediction. For Loeb, this suggested it was not merely an interpretation made after the fact. For other scientists, that was not enough. Matching a feature does not validate an entire model, and complex systems can produce similar results through different mechanisms. The debate, therefore, remained open, and the reason is simple. The image shows shape, but it does not reveal substance. This is where NASA's cautious stance comes in. The agency acknowledged the rarity and unusual appearance, but emphasized that nothing observed so far requires a new category of object or a non-conventional mechanism. Within standard physics, complex patterns can emerge from combinations of solar wind, radiation pressure, uneven gas release, and orbital geometry, especially in an object coming from a different stellar environment. NASA was also clear about what current data do not show. There is no direct evidence of artificial origin, and no confirmed sign of abnormal propulsion. The problem is that, as impressive as the morphology is, it does not reveal which materials are producing the brightness. Without composition, the discussion remains stuck in interpretation. That is why, with images reaching their limits, attention turns to a type of evidence that does not depend on appearance: spectroscopy. Hubble continues studying 3I Atlas in ultraviolet light, breaking the light into wavelengths to search for chemical signatures. The logic is straightforward. If the object is behaving like a typical comet, fingerprints of familiar gases such as carbon monoxide, carbon dioxide, and water vapor should appear. Finding those signatures would not eliminate the visual strangeness, but it would place the story on solid ground. Known materials, known processes, in a rare visitor. The most decisive scenario is the opposite. If those signatures are weak, absent, or incompatible with the observed brightness and structure, the most comfortable explanation collapses. That does not immediately prove something else, but it forces science to narrow hypotheses and search for alternative mechanisms. That is the power of spectral data. They impose limits. They define what can and cannot be happening. Until those results are complete, everything remains provisional. 3I or Atlas may end up being an interstellar comet with unusual geometry and timing. It may also reveal gaps in models that work well for solar system comets but need refinement for visitors from outside. Either way, that is what is at stake, separating appearance from cause. At the end of this observation window, some facts remain firm. 3I Atlas survived its closest encounter with the Sun. It displayed a stable, glowing teardrop structure. It showed an antitail pointing toward the Sun, rare, bright, and dominant. For some scientists, this pushes what we expect from fragile comets under extreme heat. For others, it still fits within what known processes can produce, provided the right data confirm the composition and material dynamics. And now I want to hear from you. Does this look like just a rare case of perfect geometry and gas release under unusual conditions? Or do you think we are looking at an object that will force us to rethink part of what we understand about interstellar comets? Leave your opinion in the comments, like the video, and subscribe to the channel, because the next measurements may be exactly what decides this story.